Okay, today is Thursday, January the 14th. AP Chemistry at Spain Park High School. So we're going to be working on these problems 44 through 46, 55 through 58, just trying to make sure that we have the right answers and then ask any questions that you might have on those. Okay, those of you at home, follow along in your textbook. I'll read the problems out loud, but you can open your textbook and follow along on these problems that we're going to do. So, number 45. Pardon me, try this again. Number 44. Consider the following reaction. 2CH3OH. Does anybody know what the name of that compound is? You don't have to know it, but does anybody know what CH3OH is? If it's got an OH on it, do we know what kind of compound it is? Okay. Normally we would think that an OH is a base. Okay. But when it's on a carbon, that makes it an alcohol. And with only one carbon.
You're scheduled for an 8:30 class meeting. Please report to the theater at this time.
When there's only one carbon, it's methanol. The most common alcohol is ethanol with two carbons, C2H5OH. But anytime it has an OH on a hydrocarbon, it's an alcohol. That's not important for solving this. It's just kind of something I'll throw out there, just a little extra freebie for your money. Okay? So we look at delta H. So I see that it's got a positive sign. Delta H has a positive sign on it. So what does that mean? Is the reaction exo or endothermic? Endothermic. If you were to put that delta H into the equation, where would it go on the equation? On the left side as a reactant. Okay, because you're adding heat to it to make the reaction occur. Okay? Calculate the amount of heat transferred when 24 grams of CH3OH is decomposed by this reaction at constant pressure. So again, I'm going to calculate, this is a stoichiometry type problem. This 252.8 kilojoules, that's my conversion factor. So I'm going to start with 24 grams CH3OH. I have to convert it to moles because that's a kilojoules per mole. So I'm going to say 1 mole over the molar mass, 12, 16, and 16 is 32. If you want to carry out, it's going to be 32.04 if you use more digits. Okay? Now here's the point that you need to really know. All right? That when you're looking at this, this is kilojoules per 2 moles of the methanol. Okay? It's this many kilojoules when 2 moles of methanol react. Okay? So when we go and use that conversion factor then, we're going to say 252.8 kilojoules per 2 moles of methanol. That's the most important thing here. So now moles of methanol cancel and we end up with kilojoules, and what does that turn out to equal to 3 sig figs? 94.7, and it's positive, meaning that that's how much energy to make 2 moles, or pardon me, to make 24 grams of the methanol to decompose, you're going to have to put in that much energy. Okay? So when you're given the delta H, that is your conversion factor. Just like molar mass takes grams to moles, the heat of the reaction takes kilojoules and moles. So 45. When solutions containing silver ions and chloride ions are mixed, you get silver chloride. Calculate the delta H for the production of 0.45 moles of AgCl by this reaction. Again, we have the negative 65.5 kilojoules per 1 mole. Each one's a 1. So we can just use that directly. So this one's super easy. 0.450 moles of, what do they give us? AgCl times the negative 65.5 kilojoules for every 1 mole. And then we multiply that out and we get negative 29.5 kilojoules. And again, the negative implies what? Exothermic. So what do we expect to happen to the solution when I put Ag plus and Cl minus in there together?
It's hot.
It gets hot. Okay, temperature goes up. It's exothermic. That heat that's being released by the reaction. Okay, it's the lattice energy. Okay, the lattice energy, we talk about how much energy it takes to break the AgCl, but that's the energy you put in. The same amount of energy is released when it comes back together. Okay? So, B, calculate for the production of 9 grams of AgCl. So, what's the only thing we have to do differently? Convert the 9 grams to moles, right? So it's 9 grams AgCl times the molar mass of 1 mole, 143.35? 32? 43. Times the negative 65.5 kilojoules per 1 mole. And that all equals negative 4.11, okay, kilojoules. So not a whole lot of heat's going to be released. Okay? Now C is more of a thought question. Oh, no, it's not. I thought this one. Calculate, so now what's going to be different here on when 9.25 moles of AgCl dissolves in water? How does that relate to this reaction? So what, Anna? It's going the other way. Now we're dissolving when we're looking at this reaction, now we're dissolving the AgCl to make it break apart. So what's that do to delta H? Makes it positive instead of negative. That's the only thing that's going to be different on this one. You do everything else the same. You have moles, but you're just going to multiply by the positive 65.4, 65.5. And so what does that come out to? This times that. Well, it's kilojoules per, 1 mole. And what does that come out to?
6.06 times 10 to the negative 3.
Negative 3?
2.
Negative 2 kilojoules. But it's going to be positive and not negative because we're going the other direction. Okay? Am I doing okay as far as getting it lined up? All right. So, be careful because a lot of times AP question will do that. They'll reverse it on you just to kind of see. And all we do is change the sign. All right, so let's look at number 46. At one time, a common means of forming small quantities of oxygen gas in the lab was to heat KClO3. I still do this lab some to produce the oxygen gas. And we measure the percent, I think we did it actually at the beginning of the year to measure the percent oxygen in KClO3. Okay? For this reaction, calculate the delta H for the formation of 1.36 moles of O2. So again, the key on this problem is using the delta H of the reaction, but knowing that it's per 3 moles of O2. So we have, we're looking at this, 1.36 moles. So I'm going to use my conversion factor of negative 89.4 kilojoules, but it's per how much? 3 moles of O2. That's the most important part of this. So then we multiply that out and get 40.5 kilojoules. Okay, so that's A. 10.4 grams of KCl. What's the only difference? Well, how are we going to do this one? 10.4 grams of KCl. Okay? So the only thing that's going to be different now is it's going to be 10.4 grams. I'm going to convert to moles using the molar mass of KCl. But then I'm going to say negative 89.4 kilojoules per 2 moles of KCl. All right? You all seeing that? So it's just going to be, it's going to be 10.4 divided by, what's the molar mass at? 35.45 and then 39.1. 74.55. So 10.4 grams of KCl times 1 mole, 74.55 grams times negative 89.4 kilojoules over 2 moles KCl. And all that equals negative 6.24 kilojoules. Okay? So again, all of these problems, the whole key, these are all stoichiometry. We talked about 5 different ways of calculating delta H. These are all the stoichiometry ways of calculating delta H. Okay? So then when we go to 46C, this is more of a thought question, and it says the decomposition of KCl3 proceeds spontaneously. What is that word, spontaneously? We're going to talk about that at this last part of the unit. What do you think the word spontaneously means? Okay, immediately, that's kind of what the natural instinct is for the definition. It's not exactly quite right. Okay, if we want to be spontaneous, okay, that means we're not going to plan an event, right? We're just going to do something on the spur of the moment. A spontaneous reaction is one that proceeds on its own without provocation, without planning, without having to do anything. Now, what it doesn't mean is it doesn't mean fast. Okay? So the word spontaneous simply means it will happen under ordinary conditions. This paper right here is burning spontaneously. Over time, it's going to end up looking like this, nice and yellow. Looks like it's been in a fire. It's burning spontaneously, but very, 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 very slowly. Okay? So spontaneous means it occurs on its own, but doesn't necessarily mean fast. Sometimes it's fast, but other times it's not. So, if it's spontaneous, happens all on its own, that means it's going from a less stable to a more stable state. It's releasing this much energy. So, do you think it's going to happen the other direction? Do you think if it's releasing energy, is it going to want to come back the other way? No. Generally speaking, again, just like we changed the sign, if a reaction is spontaneous left to right, it's going to be non-spontaneous right to left. That's why it's going left to right. Okay? So just generally speaking in a reaction, if something is spontaneous one way, it's going to be non-spontaneous the other way. And we're going to calculate, some of these problems talked about delta S and delta G. Delta G is really going to be the determiner of the spontaneity of the reaction. And it's a relatively easy thing to measure. Okay, so the answer basically is no. All right, so let's look at 55. 55, I can't see it on the glasses. There we go.
just sit up there so you don't have to keep.
No, that's fine.
Okay.
I don't mind. Just kind of keep eyeballing, make
If
sure
you
I'm
wanna-
just,
If you wanna just move it here and I can move it here, either way.
yeah, we'll see. I'll keep adjusting. 55, now, notice that 55 says, when a 6.5 gram sample of sodium hydroxide dissolves in 100 grams of water in a coffee cup calorimeter. So what type of problem do you think this is over 5 types of, problems? That's a calorimeter problem, okay? That's a pretty good indication it's gonna be a calorimeter problem, which is very similar to the lab that we just did. So in a calorimeter problem, what do we know? Equation we're gonna use.
Q loss equals negative Q gain.
Q lost is gonna equal negative Q gained, okay? So, the reaction is what's losing the heat. The water in the calorimeter, the solution in the calorimeter is going to be the one gaining the heat. So it's going to equal the negative mass of the solution times specific heat of the solution times change in temperature of the solution. Okay? So, what's the mass of the solution going to be? That's exactly right, because we have 100 grams of water and the 6.5. We're putting this in to the water, therefore the whole solution is going to be 106.5. Just like in the lab yesterday, okay, or Tuesday, we ended up putting the 2 grams of sodium hydroxide in the 100 grams of water. We measured the whole mass of the solution because that's what's going to gain the heat. All right, we always assume the specific heat is the same as that of water, which is 4.184. And then we look at the temperature change, 21.6 to 37.8. And it's always going to be T final minus T initial. So we just plug it in, negative 106.50 grams, 4.184 joules per gram degree Celsius, times the final minus the initial 37.8 degrees minus 21.6 degrees. And all of that turns out to equal 7,220, okay, and that's going to be a negative kilojoules. Is that what y'all got?
Yeah, I put in kilojoules, that's in.
But it's
that's-
7.2 kilojoules.
Yeah, yeah. It'd be 7.22.
7.22. We want to have, 4 sig figs, 4 sig figs, but what do we get when we subtract this? You get 16.2, right? That's 3 sig figs. So that's going to limit this to 3 sig figs. Pardon me, it's 70,000, that's right, that's joules is equal to negative 7.22 kilojoules. Sorry, that's where the confusion lies. All right, so that's A. B is the part that's really important. Calculate delta H in kilojoules per mole of NaOH. Okay? Now we have to know that NaOH, we're dissolving it in water. This is exactly what we did in the lab. What's it going to dissociate into? Na plus and OH minus. Okay? So we're dealing with 1 mole. So we want kilojoules per mole. So this delta H right here is per how much?
Mole of reaction.
No. Well, how much sodium hydroxide? 6.5 grams. Okay? So when we're doing this now, my conversion factor now is negative 7.22 kilojoules per 6.5 grams. Because this is how much heat was released when 6.5 grams dissolved. So I'm going to start with how much, I just need to change it to kilojoules per mole. So I'm going to have negative 7.22 kilojoules per 6.5 grams of NaOH. Now the point that I really want to stress is this is where we only use the solute, the reactant. In mass, we use both. This is always the confusing thing. Which mass do I use? When you're talking about the change in temperature of the solution, you use the overall mass of the solution. But when it's kilojoules per mole of the reactant, per mole of NaOH or mole of Na+, you just use however much of that you have. So how do I change this to kilojoules per mole? Molar mass, which is 40, I think 40.00, isn't it? Okay, so grams are going to cancel, and this number is going to turn out to equal negative 44.4 kilojoules. Okay, this is the type of reaction, this is the type of problem you need to be able to do for the quiz tomorrow on your Hess's law and the calorimetry. Taking the grams that we dissolved and figuring out what it's going to be in kilojoules per mole. Okay? But it's just going to be used in molar mass. But again, this value is per the 6.5 grams that dissolved. And then lastly, that was lastly. Okay? So this calculation on the AP test is very, 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 very common. Okay? This is one that really needs to be bolded, starred. We need to know how to do this well. All right, 56. Getting blurrier and blurrier. I don't think I'll be able to do anything about that. I'm going to deal with this, but I'm going to solve it right here. When 4.25 gram of ammonium nitrate, 4.25 grams, dissolves in 60 grams of water, in a coffee cup calorimeter, again, there's my clue that, hey, I'm going to be using the Q loss equals negative Q gain. The temperature drops. So what type of reaction is this? Endothermic. So what do I expect my sign of delta H of this reaction to be? It's going to be a positive delta H. So, it's the exact same problem as this one. So, Q lost. Now, the reality is it's Q gained by the water, but it doesn't matter where the negative sign. I always use the same thing, equals negative Q gained. Okay? And so, we can say again, delta H of the reaction is equal to negative times, what's the mass going to be? 64.25 times 4.184 joules. But this time it's T final minus T initial, so it's 16.9 degrees minus 22.0 degrees. So the delta T turns out to be negative. This negative and this negative make it a positive. So the delta H of the reaction is positive. That's why it doesn't really matter which one you call lost or gained. It's just they're the negative of each other. And so you can put it in either way. So, but technically, the water is gaining. In this case, the water's losing heat, but because the reaction's giving it off. But again, Q loss equals negative Q gain works no matter what, endo or exo. So the delta H of the reaction is equal to, this turns out to be, 5.1? So 2 sig figs, what do we get? 1,400 joules positive, which is equal to 1.4 kilojoules. Okay? So that's part A. Is there a B?
I think you have to do the symbol.
No, they want delta H. They combined it all into one. Okay, that's what I was looking for. Okay, so this is the delta H of the reaction, but this is 1.4 kilojoules per how much? 1.4 kilojoules per 4.25 grams of the NH4NO3. Okay, so then we just go again times the molar mass of this, which is 28 plus 4 is 32. 32 and 48 is equal to 80. Do we get 80.06? 5? Yeah, 6, because each one of these is 01 and this is an 01. So 80.06, 80.06 grams over 1 mole. Again, this is the most important thing to get out of this problem. That when you go into kilojoules per mole, if the reaction is kilojoules per however much reactant, and then you go to moles, we just do this, so what's that come out to? Anyone? No one trusts their answer, or we didn't do it this way?
26.35.
26, well, we need just 2 sig figs, so 26.
Yeah.
So it's gonna be positive 26 kilojoules per mole. We good with that? So our 2 types of problems we're working on so far are stoichiometry problems and calorimetry problems. Now the next 2 are slightly different. Same concept. Okay, so we already answered B. Is this process endo or exothermic? It was endothermic. Okay, I'm going to save myself. Okay, so now a 2.200 gram sample of quinone is burned in a bomb calorimeter whose total heat capacity, okay, total heat capacity
The volume's not on the screen.
did it just stop?
No, it's just like.